All right, now we're still building frequency distribution graphs for data that came from a sample, but what do we do if our data was either nominal or ordinal instead? Remember, those are lower levels of measurement. Again, there are multiple options. The only one your book talks about will be the only one that I bothered to address here, is the bar graph. Oh, I keep forgetting to switch that back to a 3. The bar graph. So if we're pulling our data from a sample and it is measured at the nominal or ordinal levels, we build a bar graph. So the first step is to get your workspace set up, your graph space. This is exactly like the histogram, no difference at all. So proportions, numbered, labeled, it's exactly the same. So now, with the graph made, with a blank graph space set up, we can start to fill it in with our data. So again, there are 2 ones. So I go over to the raw score of 1 up to the frequency of 2. There are 3 2s, so over to 2, up to 3. 5 3s. 3 4s. And 1 5. So it is almost exactly the same thing as a histogram, except now there's space between the bars. Because often, not always, but often nominal and ordinal data is discrete. Remember, that means it's either this or it's that. It's either it's heads or it's tails. It's either true or it's false. It's either A, B, C, or D. It's either this major or that major. There's no in-between values. So this is showing us that the in-between these, it's a no man's land there. There's nothing that exists there. I shade these in roughly just because it can be tricky for the eye to figure out if you don't, is it a bar or is it the space between the bars? So it just makes it easier to read. But it accomplishes the same basic job here. And so that's the difference. Like I said, some of these terms are used differently. You could be in a different class with a different book and different teacher, and they might tell you that a bar graph it doesn't matter if the bars touch or not, it's when the bars go sideways. And a histograph doesn't matter if they touch or not, it's when they go up or down. So there are other uses. This is not written in stone, but this is how most of us in the field use these terms. But again, not quite universal. Excuse me. So next up for us then, we are done dealing with graphs for samples. So now it's time to talk about graphing for populations of data. As you hopefully remember from chapter 1, populations tend to be really large. So our approach to graphing them is going to be a little bit different. It's usually too much information and missing information. Remember, we rarely get to the entire population measured at once to do the kind of graphing we've been doing. So we're going to find 2 major differences between population graphs and sample graphs. One of the differences we're going to see is that it uses what we call relative frequencies. When we say something is relative, that means it has meaning through comparison. So in almost any usage of the word, that's what relative is about, that it is meaningful only through comparison with something else. Now, if we're dealing with data from a population, again, we're not going to probably have all of it. Therefore, we can't get an exact count of every score. We don't know it. What we can say is, looks like there's about twice as many of these scores than those scores. Looks like there's about 1/3 less of these scores than those other scores. We can talk about more or less proportionately by comparison, but we can't say there's 32 of that score and there's 27 of that score. We can say they're roughly the same amount of scores, or this much more or this much less. So we can compare, but we're not going to have an exact frequency count. The other thing is that we are going to use smooth curves. So remember when we did the frequency polygon, the polygon, I said connect those dots with as straight a line as you can that you can manage. Because if the lines are smooth, that represents estimation. That's representing we don't have the exact counts, but we're figuring it goes in that area somewhere. It's probably in that neighborhood. So the smooth curves are representing just that, sort of a trend and estimation through. So those are the primary differences between how we do this for populations and how we do this for samples. Now again, you could, if it's a small population, you could use one of those earlier graphs. If it's an enormous sample, I suppose you could do it this way, but usually wouldn't. So what we're typically going to find here I'm just kind of building a generic example. We don't need any real specific data for this per se. But we're going to have a frequency axis, and we're going to have a raw score axis. Again, we would label this specifically if we knew what it was. Let's say we knew it was IQ scores. I'm going to call it IQ scores. And so I do have some numbers to plug in there. But we're not going to number this. Remember, we're going to have relative frequencies. So I don't know what the exact count of anything is. So I can't really put any numbers there. So there is a graph for data for a population. This shape is called the normal curve. Its nickname is the bell curve. Most of you have probably heard that before. This is a shape you're going to be very familiar with by the time the semester is done. A lot of our work revolves around this particular shape of a distribution. So again, we don't know of scores of an 85. How many of them were there? We don't know that exact number, but we know for scores of a 70, there were only about that many. So it, just rough eyeballing it here, it looks like there's about 70s, or about a third as many as there are 85s. Oh, it looks like there's about twice of as many people got scores of 100 as got an 85. We can talk about relative frequencies, but we can't count them exactly. So again, this overall shape, very often in the course we won't even have the axis, just the shape and working from there. But so again, this would be called a normal distribution. We're going to talk more about shape in just a moment of these. But this is the gist of making a graph for a population. So what we're going to do in the next piece here is talk about how we can read this. What can we learn beyond what I've just described? What can we learn from this graph? Really from all the graphs for the whole day. The text talks about it specific relative to these smooth curve graphs. But histograms, polygons, modified histograms, bar graphs, they all read the same way if you know what to look for. And that's what we'll tackle in the next.